In this lesson, we're going to look at the system call and how it relates to concurrency, parallelism, and non-blocking I/O. There's an important distinction that underlies the system call. That's the distinction between user space code and kernel space code. Different terminology is sometimes used. You may hear, for example, user mode code or kernel mode code, but the essential distinction is the same. And the gist of it is the following. Ordinary applications and most standard library functions, so in other words, functions that are delivered with the operating system, Windows, Unix, Mac OS X, whatever, most of this code does not have direct control over the critical shared resources in a computer system. With respect to categories, those resources are the following: processors, memory, I/O devices. In other words, an ordinary application such as a browser cannot control the screen. That's an I/O device. Instead, the browser in effect has to make a request to the operating system to display something on the screen. Kernel space code, by contrast, consists of those critical operating system routines that control the shared resources. In other words, kernel space code you can think of as the resource management code that comes with the operating system. This code is sometimes described as being pinned to memory. In other words, when you boot up the system, the kernel space code is loaded into memory and it stays there indefinitely. You couldn't afford, for example, to have it swapped in and out. It would be far too inefficient, and besides, without that kernel space code, nothing is going to happen in any case. Now, what I'd like to do is explain how this distinction between user space and kernel space code fits into what we're doing. The topic is the system call, but I'd like to explain it with an example. Suppose we have a Node.js application. So if you've not used Node.js, it's a JavaScript dialect. And in Node.js, there's a package called cluster and a function called fork. So our Node.js app, as shown here, calls the library function, in other words, the Node.js library function, called cluster.fork. Fork is the traditional name for the function that makes a copy of the currently executing process. So we run a program, suppose this is called test.js, that runs as a process. When you call fork within that application, what you're doing, in effect, is cloning the current process, the currently executing application. Those details we'll return to later. What we care about is cluster.fork calls a standard library function. So, for example, on a Windows machine, this would be called a Windows API function. On a Unix machine, this is described usually as a libc function, or sometimes a variant thereof, a glibc function, and so on. So there's a standard library function of the same name. The library functions, by the way, are written mostly in C, maybe with a little bit of assembly language. The library function then calls a kernel routine, in other words, a core operating system routine. And that core operating system routine has different names. In traditional Unix, for example, it's also called fork, a little confusing. In recent Linux distributions, that kernel routine has a different name. It's called clone. It's actually the function that does the heavy lifting. It's the function that actually makes the clone, makes the copy of the currently executing process. Now, the important thing from our point of view is this. The system call originates, is not made by, but originates in that Node.js application, the call to cluster.fork, and the library function, fork, which is also in user space, as is the application. It's the library function fork that crosses that critical boundary that separates user space from kernel space. So the library function fork makes the system call. From our point of view, the important thing is that a system call originates in user space, it terminates in kernel space. It terminates with the execution of some critical operating system routine that has control over and manages shared resources. Again, processors, memory, I/O devices. So we're going to have occasion to talk a lot about system calls when we do multiprocessing, multi-threading, and non-blocking I/O. Now, let me make two other points. The first is this. Not every library function makes a system call. For example, if you're just manipulating strings, computing their length, for example, there's a library function called strlen for string length in C. That does not make a system call. Of the 2,000 or so functions that are in a standard library, roughly speaking, 400 or so make system calls. Finally, I'd like to use this to motivate yet again the C examples. The standard libraries, the core operating system routines, are all written in C. So when you write C applications, you're about as close to the metal as you'd like to get. The only way to get any closer is to write in assembly language, which can be quite challenging. So we now have the system call out on the table, the distinction between user space and kernel space, and the system call notion and the distinction between user space and kernel space is going to prove very useful to us in the forthcoming code examples.